Imagine an object so massive, so powerful, that it could swallow our entire solar system without a second thought. A force of nature so relentless that not even light can escape its grasp. We're talking about black holes, the universe's ultimate cosmic vacuum cleaners, lurking in the darkness of space, warping reality itself. But what if I told you some of these monsters are so unimaginably large, they dwarf entire galaxies? Strap in, because today we're diving into the mind-bending world of the universe's largest black holes, where the numbers are so big they'll make your head spin. Picture this: if our sun were suddenly replaced by one of these colossal beasts, its event horizon, the point of no return, could stretch beyond the orbit of Pluto. That's not just big, that's stupidly big, and yet these titans are just the tip of the cosmic iceberg. Some black holes grow so enormous they weigh billions of times more than our sun, anchoring entire clusters of galaxies with their gravitational might. How do they get this big? What happens inside them? And could one ever creep close enough to threaten us? The universe has a way of keeping its most terrifying secrets hidden, but we're about to pull back the curtain. Over the next 30 facts, we'll explore black holes so vast they challenge everything we think we know about space and time. From the way they distort the fabric of reality to the bizarre fate of anything that falls in, this journey will take you to the edge of understanding and maybe even push you right over. So if you're ready to stare into the abyss, let's begin. Deep in the heart of a distant galaxy, over 10 billion light-years away, lurks a true cosmic behemoth, a ton 618, the largest black hole we've ever discovered. This monster tips the scales at a staggering 66 billion times the mass of our Sun. To put that into perspective, if you replaced our Sun with ton 618, its event horizon, the point where escape becomes impossible, would stretch farther than Pluto's orbit by a factor of over 1,000. Even our entire solar system would be a mere speck lost in its shadow, and that's just the beginning. Surrounding this gravitational giant is an accretion disk, a swirling maelstrom of superheated gas and dust so energetic it outshines entire galaxies. The sheer scale of ton 618's disk is almost impossible to fathom. If you could somehow stand on its edge, the light from the opposite side would take weeks to reach you. The forces at work here are so extreme that atoms are torn apart, creating a blazing halo visible across the cosmos. But here's what really bends the mind. Ton 618 isn't just big, it defies our understanding of how black holes grow. Most supermassive black holes sit at the centers of galaxies, but ton 618's size suggests it must have been feasting for billions of years, merging with other black holes and devouring stars at a rate we've never seen. Some astronomers even speculate it could be the remnant of an ancient, hyperactive quasar from the universe's early days, a time when conditions were ripe for black holes to balloon to incomprehensible sizes. Yet for all its terrifying enormity, ton 618 isn't done growing. Even now, it continues to pull in surrounding matter, stretching the laws of physics to their limits. And while it may be unimaginably distant, studying black holes like this one helps us unravel the mysteries of galaxy formation, dark matter, and even the ultimate fate of the universe itself. Finding something as enormous as ton 618 might seem like an obvious discovery, but this cosmic giant stayed hidden in plain sight for decades. The story of how we uncovered it reads like a detective novel, one where the clues were written in light that had traveled across the universe for billions of years. It all started back in the 1950s when astronomers first noticed an unusually bright radio source in the constellation Canes Venatici. At the time, they classified it simply as ton 618, a catalog number that belied its true nature. No one suspected this faint speck of light was actually a quasar, the hyperactive core of a distant galaxy powered by a black hole of unimaginable scale. Back then, telescopes weren't powerful enough to see the telltale signs. The real breakthrough came decades later with advances in spectroscopy. By splitting the light from TUN 618 into its component colors, scientists spotted something astonishing, a signature so redshifted, it meant this object wasn't just far away, it was one of the most distant quasars ever observed. That extreme distance also revealed its mind-bending luminosity. The light we see from TUN 618 left its source when the universe was less than a quarter of its current age, meaning we're witnessing the aftermath of a feeding frenzy that peaked billions of years ago. Even more fascinating is how we finally pieced together its true identity. Quasars like TUN 618 are cosmic lighthouses. Their intense radiation comes from superheated material spiraling into the black hole at nearly light speed. But it wasn't until astronomers combined observations across multiple wavelengths, from radio waves to X-rays, that they realized this wasn't just a bright quasar. The energy output suggested a black hole so massive, it challenged existing theories about how such objects could form so early in the universe's history. So why did it take so long to recognize TUN 618 for what it really was? Part of the answer lies in its sheer scale. Black holes this size were thought to be impossible in the early universe. There simply wasn't enough time for them to grow that big. It forced scientists to reconsider how black holes could merge and accumulate matter faster than we'd ever imagined. And that's what makes TUN 618 more than just a record holder. It's a cosmic puzzle, pushing the boundaries of what we know about how the universe builds its most extreme objects. The event horizon of a black hole isn't just a boundary, it's the ultimate cosmic prison wall. Once anything crosses that line, even light itself gets dragged into oblivion. But when we're talking about TUN 618, this barrier isn't just intimidating, it's ludicrously vast. Picture a sphere of pure darkness so wide, it could comfortably swallow our entire solar system like a marble. If you could somehow measure TUN 618's event horizon, you'd find it stretches over 390 billion kilometers across. That's not just bigger than our Sun, it dwarfs the entire neighborhood of planets. To put that into perspective, Neptune, the farthest major planet from our Sun, orbits at about 4.5 billion kilometers out, TUN 618's event horizon. It's nearly 90 times wider than Neptune's entire orbital path. Even if you lined up every planet in our solar system end to end, they wouldn't come close to spanning the dark maw of this cosmic monster. Here's another way to grasp the scale. Imagine traveling at the speed of light. Crossing our solar system from the Sun to Pluto would take you roughly 5.5 hours. But to traverse TUN 618's event horizon at that same speed, you'd be racing through pure darkness for over 14 days without ever seeing the other side. What makes this even wilder is how empty that space truly is. Unlike a planet or star, the event horizon isn't a physical surface, it's just the invisible point where gravity becomes inescapable. If you were falling in, you wouldn't even know you'd crossed it until it was too late. The only clue would be the universe behind you warping into a shrinking circle of light before vanishing forever. And yet, for all its mind-numbing size, TUN 618's event horizon is just the beginning of its absurdity. The gravitational forces at play here twist space-time so violently that time itself would crawl to a near standstill for anyone watching from the outside. A single minute for someone unfortunate enough to cross that threshold could equate to centuries passing in the rest of the universe. It's a place where the normal rules of physics don't just bend, they shatter completely. But here's the real kicker. Despite dominating space on an unimaginable scale, black holes like TUN 618 are paradoxically simple objects. Unlike stars or planets with complex layers and atmospheres, an event horizon hides just three defining features: mass, spin, and charge. Everything else, every atom, every scream of radiation, every doomed spaceship gets crushed into oblivion, leaving behind only a silent, perfect sphere of darkness. We often toss around terms like supermassive when talking about black holes, but Ton 618 belongs to an even more exclusive club, the Ultramassive. The difference between these categories isn't just academic, it's a cosmic chasm that redefines what we thought was possible. Let's start with supermassive black holes. These are the giants that anchor galaxies like our own Milky Way, typically weighing in at millions to billions of times the mass of our Sun. Picture a gravitational pit so deep it holds entire galaxies in orbit. That's a supermassive black hole doing its job. Sagittarius, a star, the one at the center of our galaxy, is a textbook example, clocking in at around 4 million solar masses. Impressive, sure, but still small fry compared to what's out there. Now meet the ultramassives, black holes so colossal, they make supermassives look like backyard ponds next to an ocean. These beasts, like Ton 618, start at tens of billions of solar masses and go up from there. Their scale is so absurd, early astronomers didn't even think they could exist. The math suggested there simply wasn't enough time in the universe's history for black holes to accumulate that much matter. Yet here they are, flaunting their size like cosmic celebrities. What really sets ultramassives apart isn't just their weight, it's how they warp their surroundings. A typical supermassive black hole's influence might stretch a few light years, but an ultramassive can dominate regions spanning hundreds of thousands of light years. Their gravitational reach is so vast, they don't just host galaxies, they orchestrate them, dictating the motion of stars and gas across unfathomable distances. The most mind-bending part, we're still piecing together how ultramassives grow so big. Supermassives can form from collapsing gas clouds or merging smaller black holes, but ultramassives seem to require a perfect storm of conditions: voracious feeding in the early universe, galaxy collisions that funnel entire star clusters into their maws, or even exotic physics we haven't discovered yet. Ton 618, for instance, might be the fossilized core of a primordial quasar, a relic from an era when the universe was a chaotic buffet of gas and young stars. Here's the kicker: ultramassives aren't just bigger versions of supermassives. They're a different breed entirely, challenging our models of cosmic evolution. Finding one like Ton 618 isn't just about setting records, it's a clue that the universe has ways of building monsters we're only beginning to understand. Deep in the heart of the Phoenix cluster, a cosmic glutton is shattering expectations. This isn't just another supermassive black hole. It's a ravenous anomaly consuming matter at a rate that defies logic. Every single day, this beast gulps down the equivalent of 600 Earths in gas and dust, a feeding frenzy so intense it's rewriting the rulebook on how black holes grow. What makes the Phoenix cluster's black hole so extraordinary isn't just its appetite, it's the sheer impossibility of its existence according to old models. Astronomers once thought black holes had a natural speed limit, a point where radiation from their accretion disks would push away nearby matter, cutting off their food supply. It's like trying to drink from a fire hose. Eventually, the pressure blows the water right back at you. But the Phoenix black hole laughs in the face of that limit, devouring material so fast it should technically starve itself. Yet somehow it keeps packing on mass like a competitive eater who never gets full. The numbers here are staggering. At its current rate, this black hole could double its size in a mere few 100 million years, a blink of an eye in cosmic terms. To put that into perspective, imagine a newborn baby growing to the size of Mount Everest in under a minute. The energy released by this non-stop feast is equally mind-bending. Its accretion disk blazes with the brightness of trillions of suns, pumping out enough X-rays to sterilize entire galaxies. But here's the real puzzle. Why hasn't it hit the theoretical Eddington limit, the point where radiation pressure should halt its growth? The answer might lie in the chaotic environment of the Phoenix cluster itself. Unlike quieter galactic neighborhoods, this cluster is swimming in a vast ocean of superheated gas, so dense the black hole can gorge itself non-stop. Some scientists speculate that magnetic fields are funneling material inward like cosmic conveyor belts, bypassing the usual roadblocks. Others wonder if we're witnessing a rare phase of black hole evolution, a brief window where the universe's most extreme objects reveal their true potential. What's clear is that the Phoenix black hole isn't just breaking records, it's forcing us to rethink how black holes interact with their surroundings. It's a reminder that the universe often reserves its most spectacular shows for those willing to question what they think they know. The growth of black holes isn't just a slow nibble, it's a cosmic feast where the universe serves up entire stars and galaxies on a silver platter. To understand how monsters like Ton 618 reach such mind-boggling sizes, we need to dive into the two main courses on their menu, mergers and accretion. First, imagine two galaxies locked in a gravitational tango, spiraling closer until their central black holes collide. When this happens, the resulting merger creates a single, even more massive black hole, a cosmic upgrade that's like combining two whirlpools into a tidal wave. These collisions aren't gentle, they send shockwaves through space-time, rippling as gravitational waves that we can now detect here on Earth. The math behind these mergers is staggering. When black holes with billions of solar masses combine, the energy released can briefly outshine every star in the observable universe. And because galaxies often collide in the crowded cosmic neighborhood, these mergers are like all-you-can-eat buffets for growing black holes. But mergers alone can't explain the sheer scale of ultramassive black holes. That's where accretion comes in, the process of a black hole vacuuming up gas, dust, and even stars from its surroundings. Picture a whirlpool in space where matter spirals inward at nearly light speed, heating up until it glows brighter than 1 trillion suns. This isn't just a steady drip, it's a fire hose of material. In dense regions like galaxy cores, black holes can devour the equivalent of a star per day, packing on mass at rates that defy intuition. The real kicker. Galaxy collisions supercharge this process. When two galaxies smash together, their gas clouds get funneled toward the merged black hole like water circling a drain. This creates an accretion disk so massive and turbulent, it can sustain feeding frenzies for millions of years. Some of these disks are so wide, light would take weeks to cross them, and their temperatures soar to millions of degrees, hot enough to strip electrons from atoms and warp the very fabric of space. Yet even this isn't the full story. Some black holes seem to grow faster than physics should allow, especially in the early universe. One theory suggests they bypassed the usual limits by feasting on cold, dense streams of gas that flowed like rivers into their cores. Others propose they were born big, collapsing directly from enormous clouds of primordial matter without ever being small at all. What's clear is that black holes don't grow in isolation. They're shaped by their environments, from the chaos of galaxy collisions to the delicate balance of radiation and gravity. And as we peer deeper into the cosmos, we're finding that the universe has far more ways to build these giants than we ever imagined. Quasars like Ton 618 aren't just black holes, they're the universe's most blinding lighthouses, visible from billions of light years away. The secret to their brilliance lies in the chaos surrounding them. While most supermassive black holes sit quietly at galaxy centers, quasars are in the middle of a cosmic feeding frenzy, tearing through matter with such violence that they outshine entire galaxies. Picture a hurricane where the eye is a black hole and the swirling storm is an accretion disk hotter than 1 million suns. That's a quasar in action. The physics behind this spectacle is both simple and mind-bending. As gas, dust, and even whole stars spiral toward the black hole, friction heats them to temperatures exceeding hundreds of millions of degrees. Atoms are ripped apart, creating a plasma so energetic it blasts out radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. This isn't just light, it's a scream of energy so powerful it can travel across the observable universe without fading into darkness. But here's what's truly wild. Quasars aren't just bright, they're efficient. Up to 40% of the infalling matter's mass gets converted directly into energy through Einstein's famous E=mc². Compare that to nuclear fusion in stars, which converts less than 1% of mass into energy, and you start to see why quasars dominate the cosmic stage. A single quasar can emit thousands of times more light than the Milky Way's hundreds of billions of stars combined. Yet quasars also have an expiration date. Their extreme brightness depends on a steady supply of material to devour, and over time they either exhaust their fuel or blow away nearby gas with their own radiation. That's why the most luminous quasars, like TUN 618, are relics of the early universe, a time when galaxies were gas-rich and collisions were frequent. Today, we see them as flickering beacons from the past, their light frozen in time, offering a glimpse of an era when black holes ruled the cosmos. What makes quasars like TUN 618 special isn't just their power, it's their role as cosmic signposts. By studying their light, astronomers can map the structure of the universe, measure its expansion, and even probe the nature of spacetime itself. They're not just monsters, they're tools, helping us decode the universe's grandest mysteries from the echoes of their ancient fury. Standing near the edge of a black hole like TUN 618 wouldn't just be dangerous, it would throw your entire experience of time into chaos. Thanks to Einstein's theory of relativity, gravity doesn't just bend space, it warps time itself. The closer you get to an ultramassive black hole's event horizon, the slower your clock ticks compared to someone watching from afar. It's like the universe hits the brakes on your reality while everyone else speeds ahead. Picture this: if you could hover just outside TUN 618's event horizon, let's say with some impossibly advanced spaceship, your experience of time would stretch into surreal extremes. For every minute you spend there, decades or even centuries might pass on Earth. A single orbit around this black hole could mean returning to a home planet where everyone you knew has been dead for generations. The effect is so dramatic that if you pointed a telescope back at Earth, you'd see civilizations rise and fall in fast forward, like watching a time-lapse of history unravel at lightning speed. This isn't just theoretical, we see time dilation in action across the cosmos, just on smaller scales. GPS satellites orbiting Earth, for example, have to account for tiny time discrepancies caused by our planet's gravity. But near an ultramassive black hole, the effect isn't a minor adjustment. It's a full-blown temporal earthquake. The gravitational pull is so immense that light struggling to escape loses energy, stretching its wavelengths into the red part of the spectrum, a phenomenon called gravitational redshift. It's as if time itself is being sucked into the black hole along with everything else. The most mind-bending part, from your perspective near the event horizon, time would feel normal. Your watch would tick at its usual pace and your heart would beat as it always does, but the universe beyond would become a frenzied blur. Drop a clock into the abyss and distant observers would see its hands freeze as it approaches the horizon, never quite crossing from their point of view. Meanwhile, for the doomed clock, time marches forward until it's shredded by tidal forces. This asymmetry isn't a glitch, it's a fundamental feature of how gravity and time intertwine. Black holes don't just trap matter, they distort the very fabric of cause and effect. For civilizations advanced enough to harness this, orbiting a black hole could act as a time machine to the future. But there's no going back. Once time slows down for you, the rest of the universe races ahead with no rewind button. It's a one-way trip into the unknown where the laws of physics twist into something stranger than fiction. Black holes like TUN 618 present astronomers with a cosmic mystery. How did these titans grow so enormous when the universe was still in its infancy? According to our current models, black holes should take billions of years to accumulate such staggering mass through steady feeding and mergers. Yet we're finding ultramassive black holes that were already fully formed when the cosmos was less than a tenth of its current age. It's like discovering a 500-pound toddler. The numbers just don't add up. The heart of the problem lies in what scientists call the Eddington limit, a sort of speed limit for black hole growth. Imagine trying to fill a bucket with a fire hose. At a certain point, the water pressure pushes back so hard that no more can enter. Similarly, as matter falls into a black hole, the intense radiation from its accretion disk should blast away surrounding gas, cutting off its own food supply. Calculations suggest even the greediest black holes can only grow at a certain rate before they hit this natural ceiling. Yet the existence of early monsters like Ton 618 suggests some black holes weren't just breaking the speed limit, they were outright ignoring it. So how did they do it? One theory points to supermassive seeds, black holes that didn't start small but were born already weighing thousands of solar masses. These could have formed directly from the collapse of enormous gas clouds in the early universe, skipping the slow growth phase entirely. Another possibility is that black holes went through periods of super-Eddington feeding, where dense, cold streams of gas flowed into them like a cosmic conveyor belt, bypassing the radiation pressure that would normally keep growth in check. But the most tantalizing idea involves galaxy collisions. In the chaotic early universe, galaxies merged far more frequently than they do today. Each collision would funnel torrents of gas toward the central black hole, creating temporary feeding frenzies where the usual limits didn't apply. Picture a buffet where the plates keep magically refilling faster than you can eat. That's what these black holes might have experienced during their wild youth. What makes this puzzle so crucial isn't just about setting records, it challenges our entire timeline of cosmic evolution. If black holes could grow this fast, it implies the early universe was far more dynamic and extreme than we've assumed. Perhaps matter was distributed differently, or physical constants operated under slightly different rules. Every ultramassive black hole we find is a clue, whispering secrets about a time when the universe was young, violent, and utterly unlike anything we see today. Nestled at the heart of IC 110-1, the largest known galaxy in the observable universe, lies a gravitational titan so enormous it makes even Ton 618 seem modest by comparison. This hidden monster, weighing somewhere between 40 and 100 billion times the mass of our Sun, represents one of the most extreme objects nature has ever crafted. To grasp the sheer absurdity of its scale, picture this: if you replaced our Sun with IC 110-1's central black hole, its event horizon would extend farther than the entire Oort cloud, that distant shell of icy debris marking the solar system's edge. The galaxy hosting this beast is no less extraordinary. IC 110-1 spans over 6 million light-years across, more than 50 times wider than the Milky Way. Its diffuse golden glow contains trillions of stars orbiting the black hole like moths circling a cosmic flame. The galaxy's core is so densely packed that if you stood on a hypothetical planet there, the night sky would blaze with the light of millions of stars visible to the naked eye, a view that would make our starriest night seem pitch black by comparison. What's truly baffling about this black hole isn't just its size, but how it exists at all. Current theories suggest black holes can't grow indefinitely. They eventually reach a point where their own radiation prevents further feeding. Yet IC 110-1's monster seems to defy that limit, having somehow gorged itself to near cosmic proportions. One possible explanation lies in the galaxy's violent past. Astronomers suspect IC 110-1 formed through countless collisions, each merger funneling more stars and gas toward its center like water swirling down a drain. Over billions of years, this never-ending feast may have allowed its black hole to balloon beyond what we thought possible. The black hole's impact on its surroundings is equally mind-bending. Its gravity warps the orbits of stars thousands of light-years away, creating a vast, dead zone where few stars can maintain stable paths. The tidal forces near its event horizon are so strong that they could stretch a human molecule by molecule in a process called spaghettification before they even cross the point of no return. And yet, despite its terrifying power, this black hole is curiously quiet. Its accretion dimmed by time, now shining with barely a whisper compared to the blazing quasars of the early universe. Studying IC 110's hidden giant gives us more than just cosmic records to marvel at. It challenges our understanding of how galaxies and black holes co-evolve, suggesting there might be undiscovered mechanisms that allow black holes to grow even larger than we've imagined. Some theories even propose these ultra-monsters could be the anchors of future galaxy superclusters, their gravity shaping the large-scale structure of the universe itself. One thing's certain: wherever we find limits in astrophysics, the universe seems determined to show us exceptions lurking in the shadows. When two ultramassive black holes collide, the universe itself trembles. These aren't just quiet mergers, they're catastrophic events so powerful they warp the fabric of space-time, sending ripples across billions of light-years. In 2019, the LIGO and Virgo observatories detected something extraordinary: gravitational waves from an event dubbed GW 19521, the echo of two black holes smashing together when the universe was half its current age. The numbers alone are staggering: a 66 solar mass black hole merging with an 85 solar mass counterpart, forming a new monster weighing 142 times our Sun's mass. The energy released in that collision defies comprehension. For a fraction of a second, the merger outshone every star in the observable universe combined, packing more power than all the light emitted by every galaxy in existence. But here's what's truly wild: we didn't see this event, we heard it. Gravitational waves stretch and compress space itself as they pass, meaning detectors like LIGO essentially listen to the cosmos by measuring microscopic changes in laser beams over 4-kilometer distances. The signal from GW 19521 lasted just 1/10 of a second, a cosmic drumbeat vibrating at the lowest frequencies human instruments can detect. This particular merger rewrote the rulebook in two ways. First, it proved black holes could form in the forbidden zone between 100 and 1,000 solar masses, a range theorists once thought impossible due to how stars collapse. Second, it revealed that black holes might spin in wildly misaligned orbits before merging, like two tops wobbling chaotically before crashing together. The resulting gravitational wave, chirp, a rising frequency as the black holes spiraled inward, carried signatures of these violent dynamics, offering clues about how such giants form and pair up. But GW 19521 isn't alone. Every few minutes, another black hole merger rattles space-time somewhere in the cosmos. Some involve pairs weighing just a few solar masses. Others, like the potential mergers of ultramassive black holes in galactic cores, would shake the universe far harder. Future detectors, like the space-based LISA mission, aim to catch these deeper tremors, low-frequency waves from collisions so massive their ripples take years to oscillate. Imagine listening to the slow, cosmic heartbeat of black holes millions of times heavier than our Sun, their mergers unfolding over months rather than milliseconds. What's exhilarating is how young this field remains. Gravitational wave astronomy has existed for less than a decade, yet it's already revealing a hidden symphony of black hole collisions. A universe far more dynamic and violent than our telescopes alone could ever show. Each detection peels back another layer, exposing the secret lives of these invisible giants as they dance, spiral, and collide in the darkness. What if the universe's most terrifying objects weren't always hidden? The naked singularity hypothesis throws a wrench into everything we thought we knew about black holes by proposing some ultramassive monsters might not have event horizons at all. Instead of a dark void shrouded by an invisible boundary, these cosmic anomalies would expose their infinitely dense cores to the universe, a singularity without its cosmic cloak. The idea stems from Einstein's equations themselves. Normally, general relativity predicts that collapsing stars wrap their singularities, points of infinite density, in event horizons, creating the black holes we're familiar with. But mathematics allows for another possibility. If a collapsing object spins fast enough or carries the right charge, it might not form an event horizon at all. The result, a naked singularity, a gravitational monster where the raw, unfiltered chaos of infinite density sits fully visible to the cosmos. Here's where it gets wild. Unlike black holes, which trap everything including light, naked singularities could theoretically let radiation escape from their surfaces. Imagine a spinning, ultramassive black hole hurling material outward with such force that it prevents an event horizon from forming. Instead of darkness, you'd see a swirling maelstrom of twisted spacetime and gravitational fireworks, where the laws of physics as we know them break down completely. Detecting one wouldn't just rewrite textbooks, it would revolutionize physics. Naked singularities could serve as natural laboratories for studying quantum gravity, offering clues about how to unite relativity with quantum mechanics. Their exposed cores might emit unique radiation patterns or distort background starlight in ways no black hole could replicate. Some theorists even speculate they could be portals to other universes, their lack of an event horizon leaving a doorway permanently ajar. Yet the universe seems suspiciously devoid of these exposed monsters, leading physicists to propose the cosmic censorship hypothesis, the idea that nature abhors naked singularities and always wraps them in event horizons. It's as if the cosmos has a built-in modesty filter, preventing us from peering directly into the heart of infinity. But what if we're just not looking properly? Some astronomers suggest certain quasars or gamma-ray bursts might actually be naked singularities in disguise. Others speculate that colliding black holes could temporarily expose their singularities during violent mergers, creating fleeting windows into the unimaginable. Until we spot definitive proof, these cosmic exhibitionists remain one of theoretical physics' most tantalizing what-ifs, a reminder that even the universe's most extreme objects might still have secrets left to reveal. One of the biggest mysteries in modern cosmology isn't just how black holes grow. It's what invisible forces might be helping them along the way. Enter dark matter, that elusive substance making up 85% of the universe's mass, yet refusing to interact with light or ordinary matter. Scientists have long wondered, could this shadowy cosmic ingredient be secretly feeding black holes, accelerating their growth in ways we can't see? Or even more intriguing, might black holes themselves be connected to dark matter's very existence? The first theory suggests dark matter could act like cosmic fertilizer for black holes. Unlike normal matter, which gets heated up and emits radiation as it falls toward a black hole, dark matter would plunge straight in without a trace. No glowing accretion disk, no telltale X-rays, just pure, silent consumption. Some simulations show that in dense regions like galaxy centers, dark matter could pile up in spikes around black holes, creating an invisible buffet that lets them pack on mass far faster than visible matter alone would allow. Imagine a black hole growing obese on food you can't see, its waistline expanding without a single calorie ever lighting up our telescopes. But here's where it gets twisty. If dark matter really does help black holes balloon to ultramassive sizes, why don't we see more evidence of this process in young galaxies? Observations of early quasars like TUN 618 suggest they grew too fast even for dark matter-assisted scenarios. This has led to a radical counter-proposal. Maybe certain types of black holes are dark matter. Primordial black holes, hypothetical objects formed in the universe's first chaotic moments, could theoretically make up a portion of dark matter's missing mass. These wouldn't be the black holes we know from dying stars, but tiny, ancient ones peppered throughout space like invisible buckshot. The plot thickens when you consider recent observations of surprisingly heavy black holes in sparse regions of space. These lone wolves shouldn't have enough ordinary matter around to grow so large, leading some researchers to suspect they're feeding on dark matter halos, vast, unseen cocoons of material that dwarf their host galaxies. Other models propose that dark matter particles could collide and annihilate near black holes, producing energy that indirectly fuels their growth. It's a cosmic shell game where the rules keep changing. Yet for all these tantalizing ideas, hard evidence remains frustratingly out of reach. Dark matter's refusal to interact with normal matter makes it notoriously hard to study, while black holes famously keep their meals private behind event horizons. Future gravitational wave detectors might catch hints of dark matter's influence by spotting black hole mergers that defy standard mass predictions. Others are studying the subtle wobbles of stars near galaxy centers, hunting for gravitational tugs that could betray unseen dark matter caches. What makes this debate so thrilling is how it ties two cosmic enigmas together. Solving one could crack the other, revealing whether black holes are silent beneficiaries of dark matter's shadowy presence, or if they've been part of its mysterious identity all along. Until then, it's a reminder that even the universe's darkest corners might hold the keys to its brightest secrets. While we've marveled at black holes big enough to swallow solar systems whole, our own Milky Way harbors a surprisingly modest giant at its heart, Sagittarius, a star. Weighing in at a mere 4 million solar masses, this supermassive black hole is downright petite compared to cosmic monsters like Ton 618. If ultramassive black holes are gravitational skyscrapers, Sagittarius, a star, is more like a suburban bungalow, still impressive but playing in an entirely different league. What makes this contrast so fascinating isn't just the size difference, it's how these black holes behave. While distant quasars blaze with the energy of devoured galaxies, Sagittarius, a star, is practically napping. Its accretion disk emits just faint wisps of X-rays, a sign it's been on a cosmic diet for millions of years. At its current feeding rate, our galactic center would take trillions of years to double its mass, meaning we're living during an exceptionally quiet chapter of its existence. Yet don't let its calm demeanor fool you. Sagittarius, a star, still rules our galaxy with an invisible gravitational fist. Thousands of stars whip around it at thousands of kilometers per second, their elongated orbits tracing the black hole's influence like cosmic breadcrumbs. Some, like the star S2, complete frenzied orbits in just 15 years, reaching speeds that would send them from Earth to Neptune in under a week. These stellar speed demons are how we first confirmed the black hole's existence by watching their extreme dance around what appeared to be empty space. Interestingly, Sagittarius, a star's relatively small size, might explain why our galactic neighborhood is so stable. Unlike active quasars that blast their surroundings with lethal radiation, our black hole's milder output allows planets like Earth to exist relatively unscathed. But cosmic history suggests this peace won't last forever. When the Milky Way eventually collides with the Andromeda Galaxy in about 4 billion years, the resulting merger could jolt Sagittarius, a star, awake, potentially transforming it into a miniature quasar as it feasts on newly delivered gas and stars. This quiet giant offers astronomers something ultramassive black holes can't: a close-up laboratory for studying supermassive behavior. Recent images from the Event Horizon Telescope revealed its shadow against glowing gas, marking the first time we've seen the gateway to a black hole's abyss. Each new observation peels back another layer, proving even the universe's smaller monsters hold monumental secrets. Let's take a terrifying trip through the imagination. What if Earth suddenly found itself drifting toward a black hole like Ton 618? The first sign of trouble wouldn't be darkness or cold, but an invisible force stretching our planet like taffy. Tidal forces near an ultramassive black hole don't just pull, they create a gravitational gradient so extreme, the side of Earth facing the black hole would feel vastly stronger gravity than the far side. The result, our planet would elongate, oceans surging toward the looming abyss while mountains crumble under incomprehensible stress. This is spaghettification in action, not some abstract concept, but a violent rearrangement of matter on a planetary scale. Even before Earth crossed the event horizon, the sheer difference in gravitational pull would warp our planet into a grotesque shape. Imagine the Moon's tidal forces on our oceans, but amplified by billions. Entire continents would crack as tectonic plates are wrenched apart, magma bleeding into space as our atmosphere gets shredded into glowing streamers of superheated gas. The sky would transform into a twisted panorama, starlight bending around the black hole's shadow like a cosmic funhouse mirror. Time itself would crawl. A single Earth day might stretch into years for distant observers watching our demise. But Earth isn't the only casualty in this nightmare scenario. Nearby stars would fare just as badly, their plasma stretching into luminous filaments before detonating in bursts of X-rays. The black hole's accretion disk, already a churning storm of annihilated matter, would blaze brighter as fresh fuel rains down, potentially sterilizing entire star systems with lethal radiation. Even if our planet miraculously avoided direct spaghettification, the gamma-ray bursts and cosmic rays from this chaotic feast would scorch Earth's surface clean of life in seconds. Here's the chilling twist. For an observer on Earth's remains, the experience would be eerily calm as tidal forces overwhelm local physics. Falling toward the event horizon, you'd see the universe outside compress into a shrinking circle of blue shifted light behind you, while ahead lies only infinite darkness. The black hole's sheer size means you might cross the threshold without immediately noticing. No violent ripping, just an inexorable slide into oblivion where time and space lose all meaning. What makes this scenario so unsettling isn't just the scale of destruction, it's how it reveals the universe's indifference. Black holes aren't malevolent, they simply follow physics to its most extreme conclusions. And while Earth will never face this fate, our galaxy's central black hole is too distant and too quiet. The cosmos is full of monsters that remind us how fragile our place in it really is. Dark energy, the mysterious force driving the universe's accelerating expansion, might seem too vast and diffuse to influence something as localized as a black hole. But when you're dealing with ultramassive monsters spanning billions of kilometers, even the subtlest cosmic forces can have profound consequences. Imagine two black holes destined to collide, their gravitational dance pulling them closer over eons, only for dark energy to stretch the space between them like taffy, delaying or even preventing their merger entirely. This isn't just theoretical. As the universe expands, galaxies and their central black holes are being pushed apart faster, reducing the chances of cosmic collisions that create even larger black holes. The math gets even wilder when you consider the far future. If dark energy continues accelerating expansion unchecked, eventually even the tight bonds holding galaxy clusters together could snap. Black holes that would have merged 1 trillion years from now might find themselves stranded in lonely voids, isolated by space stretching faster than gravity can bridge. Some models suggest this could cap the ultimate size of black holes, preventing the formation of true hypergiants that might otherwise devour entire galactic superclusters. Yet dark energy's influence might not be entirely restrictive. In regions where matter is dense enough to resist cosmic expansion like the cores of galaxy clusters, black holes could still feast on nearby gas and stars long after the rest of the universe has faded into darkness. These cosmic fortresses might become the last bastions of activity in an otherwise silent, expanding void, their growth fueled by matter too close to escape. It's a paradoxical twist. While dark energy tears the universe apart on large scales, it could indirectly concentrate the resources that allow black holes to grow larger in localized pockets. The real puzzle lies in the interplay between dark energy and black hole singularities themselves. Some theoretical models propose that singularities might somehow generate or interact with dark energy, creating a feedback loop where the universe's expansion and black hole evolution are fundamentally linked. While there's no direct evidence yet, the mere possibility hints at a deeper connection between the universe's largest mysteries, one where the invisible forces shaping cosmic fate might be intertwined with the darkest objects it contains. Black holes might seem like agents of pure destruction, but they have an unexpected role: cosmic thermostats keeping entire galaxies from burning out too soon. Those powerful jets of energy blasting from active black holes don't just annihilate matter, they sculpt their surroundings with precision, controlling when, where, and how stars can form. Picture a supermassive black hole at the center of a galaxy, spewing twin beams of plasma at nearly light speed. These jets stretch for thousands of light years, carrying enough energy to vaporize planets, yet paradoxically, they're essential for galactic survival. Here's how it works. When a galaxy's core is too rich with gas, the raw material for star formation, the black hole's jets act like a pressure release valve. They blast away excess gas, preventing it from collapsing into too many stars too quickly. Without this cosmic regulation, galaxies would exhaust their fuel in frenzied bursts of star birth, leaving them barren and lifeless long before their time. The jets heat surrounding gas clouds, stirring them like a spoon in a cosmic cauldron, ensuring stars form at a steady, sustainable pace instead of in a single, unsustainable blaze. But the real magic happens in the feedback loop between black holes and their galaxies. When star formation runs too hot, the black hole's jets ramp up, pushing back against the chaos. When things cool down, the jets weaken, allowing gas to pool and new stars to ignite. It's a delicate dance, one that's kept galaxies like our Milky Way stable for billions of years. Some astronomers even compare this system to a thermostat in a house. When the room gets too warm, the air conditioning kicks in, and when it cools, the heat resumes. Only in this case, the room is an entire galaxy, and the thermostat is a gravitational monster with the power to shape cosmic evolution. We see this balancing act in action across the universe. In galaxy clusters like Perseus, black hole jets carve enormous bubbles in the surrounding gas, visible in X-ray images as vast, ghostly cavities. These bubbles prevent the gas from cooling and forming stars too rapidly, effectively putting a cosmic lid on runaway star formation. Meanwhile, in galaxies like Messier 87, the jets twist into intricate spirals, their energy dissipating in carefully controlled waves that maintain equilibrium across thousands of light years. Yet this system isn't perfect. Sometimes the thermostat fails. When a black hole's jets are too weak, galaxies can become red and dead, their gas used up in a frenzy of unchecked star birth, leaving behind only aging stars with no new ones to replace them. Other times, if the jets are too strong, they can strip a galaxy of its gas entirely, shutting down star formation altogether. The most massive galaxies in the universe may owe their size to this very process, their black holes growing in lockstep with their stars, ensuring neither overwhelms the other. What's astonishing is that this intricate balancing act has been going on since the earliest days of the universe. Ancient quasars, blazing with the energy of supermassive black holes, likely played a crucial role in shaping the galaxies we see today. Their jets didn't just light up the cosmos, they set the rules for how galaxies live, grow, and eventually fade. So the next time you think of black holes as purely destructive, remember they're also the unseen architects, quietly maintaining order in a universe that would otherwise spiral into chaos. At the edge of observable time, when the universe was still wearing its cosmic training wheels, a black hole defied all expectations by growing into an 800 million solar mass monster. Euler's J1342 plus 0928 isn't just old, it's a relic from an era when the first stars were still blinking awake, existing a mere 690 million years after the Big Bang. To put that into perspective, this black hole reached ultramassive status before the universe had even celebrated its 700 millionth birthday. It's like finding a fully grown redwood tree sprouting from a sapling overnight. The timeline simply doesn't add up. What makes this ancient leviathan so baffling isn't just its age, but the environment it thrived in. The early universe was a sparse, hostile place, a fog of hydrogen gas still cooling from the Big Bang's afterglow. Conventional models suggest black holes need dense clusters of stars and gas to grow this large, but Euler's J1342 plus 0928 had no such luxury. Instead, it must have feasted in ways we're only beginning to understand, possibly gorging on vast streams of cold primordial gas that flowed like rivers through the cosmic darkness. Some theories even suggest it was born big, collapsing directly from an enormous cloud of pristine hydrogen without the usual star-forming preamble. The light we see from this black hole today is a time capsule from the universe's first act. Its quasar glow, redshifted to infrared after traveling 13 billion years, reveals a signature of neutral hydrogen, evidence it existed during the epoch of reionization, when the first starlight pierced the cosmic fog. That makes it more than a black hole. It's a witness to one of the universe's most transformative periods, a time when light itself was reshaping existence. Yet the most tantalizing question remains: how many more of these early giants are lurking in the shadows? Euler's J1342 plus 0928 was found hiding in plain sight, its light stretched and dimmed by cosmic expansion. New telescopes like the James Webb Space Telescope are now scouring these ancient epochs, peeling back the layers of time to reveal whether this black hole was an outlier, or if the early universe was far stranger and far more violent than we ever dared imagine. Even the universe's most voracious eaters might have their limits. While black holes like TUN 618 and IC 110's hidden giant push the boundaries of what we thought possible, scientists have long wondered, could there be a cosmic ceiling to how big these monsters can grow? This brings us to a fascinating concept known informally as the Chandrasekhar limit for black holes, named by analogy to the famous mass limit for white dwarf stars. But unlike white dwarfs, which collapse when they exceed about 1.4 solar masses, black holes might face far stranger and more complex constraints. For starters, there's the practical limit imposed by time itself. Black holes grow by gobbling up matter and merging with one another, but the universe simply hasn't existed long enough for even the greediest black holes to swallow infinite mass. Every meal requires time for gas to spiral inward, for galaxies to collide, for mergers to complete. Given the universe's current age, astronomers calculate the absolute maximum theoretical size for a black hole might be around 50 billion solar masses. But here's the twist: that's not a hard physical limit, just a "we haven't had enough time yet" estimate. Then there's the Eddington limit we touched on earlier, the point where radiation from a feeding black hole pushes away the very material it's trying to consume. While some black holes like those in the Phoenix cluster seem to cheat this limit temporarily, sustained growth requires overcoming this self-regulation. Even the most efficient feeding can't dodge physics forever, but the wildest constraint might come from an unexpected source: the expansion of the universe itself. As dark energy accelerates cosmic expansion, galaxies and their central black holes are being pulled apart faster than gravity can bring them together. In the far future, this could leave even the hungriest black holes stranded in isolated voids, cut off from new food sources. Imagine a cosmic buffet where the tables keep sliding out of reach faster than you can grab a plate. That's the fate awaiting even ultramassive black holes given enough time. Yet nature always finds loopholes. Some theories suggest that in regions dense enough to resist cosmic expansion, like the cores of galaxy superclusters, black holes might continue merging and growing well into the future. Others speculate about direct collapse scenarios in the early universe, where primordial gas clouds could have birthed black holes weighing thousands of solar masses right from the start. The most radical ideas even play with the notion of Planck stars, hypothetical objects where quantum gravity effects might prevent singularities from growing beyond a certain density, though this remains firmly in theoretical territory. What makes this question so compelling isn't just about setting records. It challenges our fundamental understanding of how the universe structures itself. If we ever found a black hole significantly larger than current predictions allow, it would force us to rewrite entire chapters of astrophysics. Until then, these cosmic giants keep pushing the limits of our imagination, reminding us that in the universe's grand story, even the mightiest forces eventually meet their match. If ultramassive black holes like Ton 618 are the cosmic equivalent of redwood trees, then their seeds must have been planted during the universe's first spring, a time so early, so chaotic that the rules of physics played out differently. The problem is straightforward. Black holes this large shouldn't exist in the early cosmos. Even if one started feasting immediately after the Big Bang, there simply wasn't enough time for it to accumulate billions of solar masses through normal accretion. This paradox has led scientists to propose two radical solutions. Either black holes were born big, skipping the awkward toddler phase entirely, or the early universe provided a buffet so rich they grew at speeds we've never witnessed since. The first theory points to primordial black holes, hypothetical objects forged in the furnace of the Big Bang itself. Unlike stellar black holes that form from collapsing stars, these would have condensed directly from the universe's seething energy when it was less than a second old. Picture cosmic soup so dense that random fluctuations created gravitational pits deep enough to trap matter before stars even existed. These primordial seeds could have weighed anywhere from a mountain's mass to thousands of suns, providing black holes with a head start that let them balloon into ultramassive giants by the time the first galaxies formed. Some might still lurk in the cosmos today, invisible except for their gravitational whispers. Then there's the direct collapse model, a scenario where clouds of pristine hydrogen gas, unpolluted by heavy elements, collapse directly into black holes weighing tens of thousands of solar masses. In the early universe, before stars had time to seed space with metals, these gas clouds couldn't fragment into stars as they do today. Instead, they'd have catastrophically imploded under their own weight, skipping star formation entirely and birthing black holes ready-made for rapid growth. It's like a cosmic cheat code, no waiting for stars to live and die, just instant black holes fresh off the cosmic assembly line. What makes these theories so compelling is how they solve multiple cosmic puzzles at once. Primordial black holes could explain not just ultramassive black holes, but also some of the universe's missing dark matter. Direct collapse seeds neatly account for why quasars like Euler's J1342 plus 0928 existed when the universe was barely 6% of its current age. Both scenarios imply that the early cosmos was a far more extreme place than we've assumed, a realm where gravity's rules bent under pressure, allowing monsters to emerge from the chaos. Yet proving these ideas is like reconstructing a crime scene 13 billion years cold. Primordial black holes would be nearly invisible unless they happen to pass between us and a distant star, briefly magnifying its light through gravitational lensing. Direct collapse seeds would have left behind chemical fingerprints in ancient gas clouds, trace elements from their ravenous feeding that next-generation telescopes might detect. Until then, these theories remain tantalizing possibilities, reminders that when it comes to black holes, the universe has always been full of surprises. The cosmic collision catalogued as GW 19521 wasn't just another ripple in space-time. It was a gravitational thunderclap so powerful, it momentarily shook the fabric of reality itself. When two black holes weighing 66 and 85 solar masses spiraled into each other, the resulting merger birthed something astronomers had never seen before, a black hole 142 times heavier than our Sun. This wasn't just a new record, it shattered the ceiling of what scientists thought possible for black hole collisions. Here's why this event rewrote the textbooks. Before GW 19521, theorists believed black holes couldn't form in the so-called mass gap between 100 and 1,000 solar masses. Stars typically leave behind black holes up to 65 solar masses when they explode, while supermassive ones grow from millions or billions of solar masses. The idea that two medium-sized black holes could collide and land squarely in this forbidden zone sent shockwaves through the astrophysics community. It was like discovering a mountain range where geologists swore only valleys could exist. The energy released in this cataclysm defies human scales. For a fraction of a second, the merger outshone every star, galaxy, and quasar in the observable universe combined, packing more power than all starlight emitted over the same duration across cosmic history. Yet we didn't see this light show. Gravitational waves, the ripples in spacetime predicted by Einstein, carried the news to Earth as an almost imperceptible wobble in lasers at the LIGO and Virgo detectors. The signal lasted just 1/10 of a second, a cosmic drumbeat oscillating at frequencies lower than human hearing can detect. What it lacked in duration, it made up in revelation. Beyond its record-breaking mass, GW 19521 surprised scientists with its spin. Most colliding black holes rotate in roughly aligned orbits like synchronized figure skaters. But analysis of the gravitational wave, chirp, the rising frequency as the black holes spiraled inward, suggested these two might have been wildly misaligned, tumbling toward each other in a chaotic dance before merging. Some speculate this hints at a violent backstory. Perhaps these black holes were flung together during a prior galaxy collision, their spins scrambled by gravitational chaos before fate brought them crashing together. The aftermath holds even more intrigue. The newborn 142 solar mass black hole got a gravitational kick from the collision's asymmetrical energy release, sending it rocketing through space at over 150 kilometers per second. Imagine a celestial cannonball, invisible except for its gravity, now wandering the cosmic dark where it might collide again, or lurk unseen until the end of time. GW 19521 is more than a record holder. It's a portal to a hidden population of intermediate mass black holes that could be hiding throughout the cosmos. Future detectors like the space-based LISA mission might uncover more of these elusive giants, revealing whether this event was a cosmic fluke or proof that the universe has been building black holes in ways we're only beginning to understand. Not every galaxy bows to the gravitational might of a central black hole. Some have mysteriously lost theirs, while others never had one to begin with. Take the ultra-diffuse galaxy AGC 2427, a cosmic ghost so ethereal that its stars barely cling together. Despite being roughly the size of the Milky Way, its mass is spread so thin that astronomers expected to find no trace of a central black hole, and they were right. This galactic featherweight challenges our assumptions, proving black holes aren't mandatory anchors for all galaxies. Then there's the bizarre case of recoiling black holes, gravitational fugitives flung from their galactic homes during violent mergers. When two supermassive black holes spiral toward collision, their final moments can unleash an asymmetrical burst of gravitational waves, kicking the newly merged black hole clear out of the galaxy at speeds exceeding 5,000 kilometers per second. Imagine a cannonball fired from a cosmic catapult, its trajectory so extreme it overcomes the galaxy's gravitational grip forever. We've spotted telltale evidence of these runaways, like Quasar 3C186, whose black hole was caught mid-escape, trailing a luminous wake of displaced gas as it hurtled through intergalactic space. But how does a galaxy cope after losing its central gravitational anchor? For some, the absence might actually prevent new stars from forming, leaving them frozen in time as cosmic fossils. Others, like certain dwarf galaxies, may have avoided growing a massive black hole altogether. their sparse gas reserves never collapsing into the dense cores needed to ignite one. These oddballs remind us that the universe loves exceptions. Rules are made to be broken, even by the laws of gravity. The hunt for these missing giants isn't just academic, it's reshaping our understanding of galactic evolution. If recoiling black holes are common, their high-speed journeys could seed the intergalactic void with invisible monsters, drifting unseen until they collide with another galaxy billions of years later. Meanwhile, galaxies born without central black holes might reveal alternative pathways for galactic formation, ones where dark matter or turbulent gas dynamics play unexpectedly dominant roles. Every blank spot on the map whispers new questions, proving that even the absence of a black hole can reshape everything we thought we knew. Silence might dominate the vacuum of space, but near a black hole, the cosmos sings in frequencies that would shatter human eardrums. NASA's sonification of the Perseus Cluster's central black hole revealed something extraordinary, a deep, resonant hum vibrating 57 octaves below middle C, a note so low it's 50,000 trillion times deeper than the limits of human hearing. This isn't just background noise, it's the sound of superheated gas churning in the black hole's gravitational grip, pressure waves rippling through the cluster's plasma like tsunamis in a cosmic ocean. The process behind this eerie soundtrack is as fascinating as the sound itself. Astronomers took X-ray data from the Chandra Observatory, showing the black hole's outbursts carving cavities in the surrounding gas, and translated those patterns into audible frequencies. What emerged wasn't random static, but a discernible tone, the result of pressure waves propagating through the cluster for hundreds of millions of years. Think of it like running a wet finger around the rim of a wine glass, except the glass is light years wide, and the vibration comes from a black hole's gravitational fist squeezing the fabric of space-time. But why does this happen? Black holes don't just swallow matter passively, they often spit it back out in colossal jets and outbursts. These eruptions punch into the surrounding gas, creating ripples that travel outward like the concentric rings from a stone dropped in a pond. In Perseus, these ripples have wavelengths spanning tens of thousands of light years, vibrating at frequencies that persist over cosmic timescales. It's a form of energy transfer so efficient, the black hole has been playing this note continuously for over 2 billion years. Here's the twist: space isn't truly silent near black holes, we just can't hear the cacophony without technological help. The Perseus sonification isn't a gimmick, it's a legitimate scientific tool. By listening to these data, researchers can identify patterns that might be missed in visual representations, like detecting subtle harmonics in the gas's behavior or tracking how black hole outbursts evolve over time. Other clusters have since been sonified, each with its own distinct acoustic signature, some rumbling like distant thunder, others pulsing with rhythmic regularity. The most haunting implication: this sound is a fossil. The note we hear today began its journey when Earth's most complex life forms were single-celled organisms. It's a reminder that black holes don't just shape space, they score the soundtrack of the universe's evolution, their vibrations echoing long after the stars that fed them have turned to dust. Black holes might be the universe's ultimate vaults, not just crushing matter into oblivion, but preserving it in ways we're only beginning to decipher. The holographic principle suggests something radical. Every bit of information swallowed by a black hole could be encoded on its event horizon, like a cosmic fingerprint pressed into the surface of space-time. Imagine throwing a book into a fire. Normally, you'd expect the words to vanish in the flames, but with black holes, it's as if the ashes rearrange themselves into a perfect two-dimensional replica of every page, preserving the story in a form we don't yet know how to read. This idea stems from one of physics' most mind-bending revelations, that the three-dimensional world we experience might actually be projected from a two-dimensional surface like a hologram. For black holes, this means the event horizon could act as a vast storage disk, etching every particle's quantum state into its fabric as they cross the threshold. The math behind this is dizzying. A black hole the size of our sun could theoretically hold more information than all the books ever written, every photograph taken, and every thought ever recorded by humanity, compressed into a flickering boundary no thicker than a plank length. But here's where it gets wild. If the holographic principle holds, black holes might not destroy information at all. They could be the universe's most meticulous archivists. When Stephen Hawking first proposed that black holes slowly evaporate through quantum radiation, it sparked a paradox. If the hole disappears, what happens to all that swallowed information? The holographic answer: the data never actually enters the singularity. Instead, it's smeared across the horizon, waiting to be teased out by future physicists armed with equations we haven't yet invented. Critics argue this sounds like science fiction. How can three-dimensional information be perfectly preserved on a two-dimensional surface? Yet experiments with quantum entanglement already hint at stranger truths. Particles linked across vast distances seem to know each other's states instantaneously, suggesting deeper layers of connectivity in the universe's code. If spacetime itself is a projection, black holes could be the Rosetta Stones that help us crack it. The stakes here are cosmic. If information truly escapes annihilation, it reshapes our understanding of reality's foundations. Time capsules from dead civilizations, the chemical blueprints of long-vanished stars, even the quantum whispers of primordial universes, all might linger in the holographic static of black holes, waiting for a civilization advanced enough to decode them. It's a haunting thought. The universe's darkest pits might also be its most luminous libraries, their shelves lined with stories we've only just begun to imagine. The first ever image of a black hole's shadow, that iconic fiery ring with a dark heart, wasn't just a triumph of human ingenuity, it was a window into the abyss. When the Event Horizon Telescope captured M87 star in 2019, the world saw proof of Einstein's predictions etched in light, that glowing ring. Superheated gas circling at near light speed, the central void, the black hole's shadow, a region where gravity bends light so severely it creates a perfect silhouette against the inferno behind it. But here's what's staggering: M87 star weighs a relatively modest 6.5 billion solar masses. If we aimed the same telescopes at ton 618, the sheer scale of its shadow would rewrite the rules of cosmic photography. M87 star's shadow spans about 40 billion kilometers, roughly the size of our solar system out to Neptune. Now picture ton 618's shadow cast by a black hole 10 times more massive. Its event horizon is so vast, the shadow would stretch over 400 billion kilometers, a darkness so expansive, light would take nearly 2 weeks to traverse it. The AHT's global array of telescopes, as groundbreaking as they are, couldn't resolve something that colossal in detail. It's like trying to photograph a mountain from its base. You're too close to see the whole thing. Yet the real magic lies in how these shadows form. A black hole doesn't just block light like a physical object. It warps spacetime so severely that photons skimming near the event horizon get trapped in twisted orbits. Some light curves around the black hole in a hairpin turn, creating that luminous ring. Other rays spiral inward, lost forever. The shadow isn't just the hole itself. It's a portal where gravity and optics conspire to paint the universe's most perfect negative space. For ton 618, this effect would unfold on a scale so grand. The entire shadow could engulf the orbits of every planet in our solar system twice over. What's equally fascinating is how these shadows reveal a black hole's spin. M87 star's lopsided ring betrayed its rapid rotation, dragging spacetime around it like cosmic molasses. Ton 618's shadow would likely show even wilder distortions, its spin potentially flinging the shadow into bizarre, asymmetrical shapes. Imagine a cosmic funhouse mirror where gravity stretches the darkness itself into a teardrop or oval. These subtle twists encode the black hole's entire history, its mergers, its feasts, its violent infancy. But there's a haunting beauty to this scale. If you could float near Ton 618's shadow, the view would defy logic. The accretion disk wouldn't just glow beneath you, it would arc overhead, curving around the black hole's gravitational lens until the entire sky became a kaleidoscope of twisted starlight and radiant gas. The shadow itself would loom like an infinite pit, a darkness so profound it makes the void of space seem bright by comparison. And all the while, time would slow to a crawl, your seconds stretching into eons for any distant observer watching your descent. The HT's snapshot of M87 star was just the beginning. Future telescopes, like the proposed next-generation Event Horizon Telescope or space-based interferometers, might one day capture shadows of even larger giants, revealing not just their shapes, but the secrets they hold about gravity's darkest corners. Until then, these cosmic silhouettes remain both a scientific goldmine and a chilling reminder of how small our place in the universe truly is. Black holes and neutron stars represent the universe's most extreme endpoints for stellar evolution. One an insatiable gravitational trapdoor, the other a city-sized atomic nucleus so dense it bends reality itself. Both are born from the deaths of massive stars, but their paths diverge spectacularly. When a star between 8 and 30 solar masses exhausts its nuclear fuel, its core collapses in a supernova so violent that protons and electrons merge into neutrons, packing a sun's worth of matter into a sphere no wider than Manhattan. The result, a neutron star, a pulsating relic so dense that a single sugar cube-sized chunk would weigh as much as Mount Everest. Black holes spawn from even more catastrophic deaths. When a star roughly 30 times heavier than our Sun collapses, no known force can stop its implosion. The core crushes past the neutron star stage, bypassing quantum limits to form a singularity, a point of infinite density shrouded by an event horizon. Where neutron stars have surfaces you could theoretically stand on, if not for the crushing gravity and lethal radiation, black holes offer no such luxury. Cross their event horizon, and you're not just dead, you're erased from spacetime's ledger entirely. The collision of these cosmic heavyweights unleashes fireworks unlike anything else in the cosmos. When two neutron stars spiral together, they trigger kilonovae explosions that forge gold, platinum, and other heavy elements in their wake. These events shine with the light of 1,000 supernovae for mere days, scattering precious metals across galaxies like cosmic treasure chests. But when a black hole joins the dance, the outcome grows darker. A neutron star falling into a black hole doesn't just explode, it's stretched into a luminous ribbon of plasma. Its material torn apart by tidal forces before vanishing beyond the event horizon in a final, silent scream. The aftermath depends on the contestants' sizes. A modest black hole slurping up a neutron star might simply grow slightly heavier, its event horizon expanding by a few kilometers. But if two roughly equal mass neutron stars collide, the resulting merger can tip the scales past stability, birthing a brand new black hole in an instant. These transformations aren't just theoretical. Gravitational wave observatories have caught them in the act. The event catalogued as GW170817 saw a black hole 25 times our Sun's mass swallowing a neutron star twice as dense, rippling spacetime with a signal that revealed details about matter's behavior under conditions no lab could ever replicate. What makes these collisions so invaluable to science is how they illuminate the boundary between the known and the unfathomable. Neutron stars serve as cosmic laboratories, their interiors potentially housing exotic states of matter like quark-gluon plasma or strange stars made entirely of strange quarks. When torn apart by a black hole, they offer fleeting glimpses into physics at the edge of comprehension. Meanwhile, the gravitational waves from these mergers carry encoded signatures of both object structures, allowing scientists to test Einstein's theories under extremes no particle accelerator could ever approach. Yet for all their violence, these events also seed the cosmos with the building blocks of life. The gold in your jewelry, the platinum in catalytic converters, even the uranium fueling nuclear reactors, all were likely forged in the crucibles of neutron star collisions billions of years ago. Black holes may erase matter from existence, but their dances with neutron stars ensure that destruction is never truly the end. Every stellar cataclysm writes new chapters in an ongoing story where death breeds creation and darkness births light. Stephen Hawking's greatest scientific controversy wasn't about black holes destroying matter. It was about them erasing the very story of that matter from existence. This is the black hole information paradox, a puzzle so profound it pits quantum mechanics against general relativity in a battle for the soul of physics. At its core lies a deceptively simple question. When a black hole swallows a book, a star, or an astronaut, is the information about those objects truly lost forever, or does the universe keep a hidden receipt? For decades, physicists assumed black holes were the universe's ultimate shredders. Once something crosses the event horizon, its properties, the spin of an electron, the arrangement of atoms in a DNA molecule, seem to vanish from reality, leaving only the black hole's mass, charge, and spin as gravestones. Hawking supercharged this idea in the 1970s by showing black holes aren't completely black. They slowly leak radiation and evaporate over eons. But here's the catch, that Hawking radiation appears totally random, carrying no fingerprints of what fell in. If the hole eventually disappears, where did the information about its meals go? This violates a sacred principle of quantum mechanics. Information can never be truly destroyed, only scrambled. Giant black holes like Ton 618 turn this paradox into a cosmic crisis. Their sheer scale means they swallow entire stars, and the intricate quantum states those stars carried states that might have encoded the history of alien civilizations or the birth cries of primordial galaxies. If that data is truly annihilated, it's not just a book burning, it's the incineration of entire chapters of cosmic history. The paradox becomes even thornier when you consider that black holes might be holograms with all swallowed information painted on their event horizons like a cosmic DVD. But how does that data escape when the whole evaporates? The debate has birthed wild solutions. Some theorists suggest information is preserved in baby universes branching off inside black holes, a multiverse rescue mission. Others propose that Hawking radiation isn't random after all, but subtly encoded with the data of everything consumed, like smoke carrying the blueprints of a burned library. Then there's the firewall hypothesis, where the event horizon becomes a searing wall of quantum chaos that fries incoming matter but preserves its information, a cosmic compromise that still gives physicists headaches. What makes this more than academic is how ultramassive black holes stretch these theories to breaking point. Their immense lifetimes, far longer than the current age of the universe, mean we can't observe their evaporation to test ideas. Their event horizons are so vast that quantum effects might play out differently than in smaller holes. And if information is preserved, where does it go when a monster like Ton 618 finally, after trillions of years, winks out of existence? The answer could rewrite not just our understanding of black holes, but the fundamental rules governing reality itself. Ironically, Hawking himself eventually conceded that information probably escapes black holes, though the how remains one of physics' greatest unsolved mysteries. Every new observation of quasars or gravitational waves offers clues, but the paradox endures as a reminder that even the universe's darkest pits might be hiding its most luminous truths. The idea of a black hole devouring the entire universe sounds like the plot of a sci-fi disaster movie, but could it actually happen? To answer that, we need to unpack the terrifying yet ultimately reassuring physics that keeps our cosmic neighborhood safe. Even the largest black holes, like Ton 618, are bound by the same universal rules that prevent them from turning existence into an all-you-can-eat buffet. First, consider scale. While ultramassive black holes dominate their galactic centers, their gravitational reach isn't infinite. Just as Earth's gravity weakens the farther you travel from its surface, a black hole's pull follows the inverse square law, diminishing rapidly with distance. For a black hole to swallow the universe, its event horizon would need to expand faster than the universe itself is growing. That's impossible because dark energy, the mysterious force accelerating cosmic expansion, is stretching space apart faster than any black hole could hope to compensate for. It's like trying to outrun a tidal wave in a rowboat. No matter how massive the black hole, the universe's expansion wins every time. Then there's the matter of competition. Black holes aren't the only gravitational heavyweights in the cosmos. Galaxies, clusters, and even dark matter exert their own pulls, creating a complex web of forces that keeps any single object from monopolizing space. Ton 618 might anchor its galaxy, but billions of other galaxies, each with their own supermassive black holes, act as cosmic counterweights. The universe is less a hierarchy and more a democracy of gravity, where no single entity gets to rewrite the rules. But what if we ignore expansion and imagine a hypothetical black hole so enormous it defies all known physics? Even then, thermodynamics steps in to spoil the doomsday scenario. Black holes evaporate over time via Hawking radiation, losing mass faster as they grow smaller. An ultramassive black hole might take trillions of years to fade away, but the process guarantees none could last long enough to consume infinity. The universe's lifespan simply isn't long enough for even the greediest black hole to finish its meal. The myth likely stems from a misunderstanding of singularity physics, the idea that black holes warp spacetime so severely they could theoretically tunnel into other regions of existence. While wormholes and white holes remain mathematically possible, no evidence suggests they'd trigger chain reactions capable of unraveling reality. If anything, the universe seems wired to prevent such calamities, with natural checks and balances ensuring black holes remain powerful but not omnipotent. So while the image of a universe swallowing black hole makes for thrilling fiction, rest easy knowing the cosmos has built-in safeguards. Black holes may be the ultimate cosmic predators, but even they answer to a deeper set of laws, one that keeps the lights on for the rest of us. The fate of ultramassive black holes unfolds on timescales so vast, they make the age of our universe seem like the blink of an eye. Even cosmic titans like Ton 618 aren't eternal. They're merely temporary knots in the fabric of spacetime, destined to unravel through processes so slow and subtle they defy human intuition. Hawking radiation, the quantum whisper that seals their doom, works its magic at a glacial pace. For a black hole weighing billions of solar masses, the evaporation process would take not billions, not trillions, but googles of years. That's a 1 followed by 100 zeros. To put that into perspective, if every star in the observable universe had counted one number every second since the Big Bang, they'd barely have scratched the surface of this unimaginable timescale. But evaporation isn't the only path. In a universe relentlessly stretching under dark energy's influence, black holes face another destiny: cosmic isolation. As galaxies accelerate apart, the chances of collisions diminish. The chaotic mergers that once built ultramassive giants become rarer, then impossible. Black holes that once ruled vibrant galactic cores will find themselves stranded in ever-expanding voids, their event horizons glowing faintly with Hawking radiation as they shed mass like slow-leaking balloons. The last supermassive black holes might drift alone in darkness for epochs longer than all of cosmic history to date, their gravitational influence reduced to faint tremors in an increasingly empty cosmos. Yet even in this desolate far future, surprises lurk. Some models suggest the final stages of evaporation could unleash fireworks. As a black hole's mass shrinks to microscopic scales, its Hawking radiation intensifies exponentially. The last seconds of its existence might resemble a bomb blast, a final burst of energy and particles carrying away the last traces of everything it ever consumed. For a monster like Ton 618, this grand finale would briefly outshine the entire Milky Way, a fleeting memorial to its former dominance. The most tantalizing question isn't how these giants die, but what they leave behind. If the holographic principle holds, their event horizons might preserve scrambled blueprints of every atom, star, and civilization they swallowed. Some theories even suggest microscopic black holes could stabilize into exotic particles, quantum time capsules holding encrypted data from the universe's youth. Others speculate that evaporating black holes might birth new universes in their death throes, their singularities twisting into cosmic eggs for realities beyond our own. One thing's certain: the era of ultramassive black holes will leave no visible monuments. Long before the last one vanishes, the universe will have transformed beyond recognition. Stars will burn out, protons may decay, and space itself will stretch until even the cosmic microwave background fades to silence. Yet in this unimaginable future, the legacy of giants like Ton 618 might persist in subtler ways, encoded in the quantum fluctuations of empty space, or woven into the fabric of whatever strange physics governs the cosmos' final act. Their story reminds us that in the grand theater of existence, even the mightiest players are temporary, their endings just as mysterious as their beginnings. For all we've learned about the universe's largest black holes, they remain some of the greatest cosmic mysteries, each discovery revealing new questions we're not even equipped to answer yet. Take their ultimate size limits. We found black holes weighing tens of billions of solar masses, but could even larger ones lurk in the cosmic shadows? Current theories suggest an upper boundary around 50 billion solar masses, based on how long the universe has existed and how quickly matter can realistically accumulate. Yet every time we think we've found the ceiling, another monster like Ton 618 shatters expectations. Some astronomers speculate that in the densest regions of galaxy clusters, black holes might merge repeatedly across cosmic time, forming true hypergiants that could reach hundreds of billions of solar masses. The problem: we lack the tools to detect them. Their event horizons would be so vast that nearby gas might orbit too slowly to produce the telltale X-rays we typically use to find black holes. Then there's the wormhole question, a tantalizing possibility straight out of science fiction. Einstein's equations allow for the existence of bridges between distant points in space-time, and ultramassive black holes seem like natural candidates to host these cosmic shortcuts. Their immense gravity warps space-time so severely that some models suggest their singularities might bend into tunnels rather than points. But here's the catch: even if wormholes exist, they'd likely be unstable, snapping shut the instant anything tries to pass through, unless some exotic matter with negative energy props them open. The wildest theories propose that advanced civilizations might have learned to stabilize these passages, turning black holes into galactic highways. But until we understand quantum gravity, this remains firmly in the realm of speculation. Perhaps the most profound unknown is how these gravitational titans influence the universe's long-term fate. We know they shape galaxy evolution through feedback loops, but could they play an even deeper role? Some cosmological models suggest that the information swallowed by black holes might eventually escape through Hawking radiation, repopulating the distant future universe with particles and energy. Others speculate that black holes could be cosmic recycling centers, their singularities birthing new universes with slightly altered physical constants, making them the engines of a vast multiverse. And then there's the chilling possibility that the universe's accelerating expansion might isolate every black hole in its own pocket of space-time, stranding them in eternal darkness as the cosmos grows cold and empty. The most humbling realization: we're likely missing entire categories of black hole phenomena because our physics isn't yet complete. Just as quantum mechanics revolutionized our understanding of atoms, a working theory of quantum gravity could rewrite everything we think we know about singularities. Do black holes preserve information in holographic patterns? Could their interiors host entirely new phases of matter? The answers might be hiding in plain sight, encoded in gravitational waves we're only now learning to decipher, or buried in the light patterns of quasars we've yet to observe. One thing's certain: the universe's largest black holes aren't just endpoints for matter. They're cosmic classrooms, challenging us to ask better questions as we stare into their infinite depths. From their birth in the fiery cores of collapsing stars to their reign as galactic overlords, ultramassive black holes like TON 618 have rewritten the rules of cosmic possibility. These gravitational titans stretch our understanding of physics to the breaking point, where time slows to a crawl, matter gets compressed into infinity, and entire solar systems vanish without a trace. We've explored black holes so vast their event horizons could swallow our planetary neighborhood whole, ancient quasars blazing with the light of 1 trillion suns, and collisions so violent they momentarily outshine the entire universe. Each discovery peels back another layer of mystery, revealing just how much we still don't know about these cosmic monsters. Consider the paradoxes they force us to confront. How can information seemingly vanish into a singularity, yet potentially be preserved on an event horizon's surface? Why do some black holes grow to billions of solar masses when the universe was barely a toddler? And what happens to the laws of physics in the swirling chaos beyond the point of no return? These aren't just academic puzzles, they're clues to the universe's deepest secrets, hidden in the last places we'd think to look. The sheer scale of these objects defies everyday logic. A single ultramassive black hole's shadow could eclipse our entire solar system, while its gravity orchestrates the dance of galaxies millions of light years away. Yet for all their power, they're also cosmic sculptors regulating star formation, seeding the universe with heavy elements, and maybe even influencing the fate of reality itself. They're destroyers and creators, engines of chaos and architects of order, all wrapped into one. As we push the boundaries of observation, from gravitational wave detectors to next-generation telescopes, each breakthrough brings more questions than answers. Are wormholes lurking in their depths? Could they be portals to other dimensions, or are they simply the universe's way of reminding us how much we've yet to learn? So now it's your turn. Which fact left you stunned? Was it the black hole that devours 600 Earths worth of matter every day, or the one that's been humming the same note for billions of years? Drop your thoughts below and keep looking up. The universe's biggest monsters still have plenty of secrets left